Hello everyone. Seems like it's everyone who want to be here right now. My name is Artem Terentyuk. I'm a lead data scientist from Quantori. Quantori is a company which is main focus on the software development, data engineering, ML engineering in life science domain, bioinformatics and everything. And today I want to introduce you how we work with EHRs, electronic health data, and how we apply different complicated neural networks and models more generally to this specific data. And here's our journey, and I will start from what is in general electronic health records and how we adopt NLP methods to work with these types of data, and after that we'll just discuss how we could improve it and to work with it generally. Okay, what is e-trust in general? Well, I suppose that everyone goes to doctor, and you know that nowadays all their work is digitalized and they put all data about you in the databases. And usually they looks like, well, some IDs, the general name, and the vocabulary for this exact type of data. Well, it could be the SNOMED, ICD-10 is most common, and that is how mostly we could imagine this data is structured. After that, it's stored in the very huge and very big databases. Usually, they are not open for everyone, but if you are a scientist, you can ask for majority of them. Well, for example, if you want to work with them, I recommend UK Biobank. It's a very huge, very big data set based on the data from United Kingdom. I suppose that 500,000 of people for 10 years, so a lot of different data. But before you will work with it, I recommend you to think about this exact data, what it consists of and how to work with it. Well, at first, we should imagine that the variety of this data is enormous. And if we'll speak about only the conditions, in ICD-10, I suppose it would be 16,000 of unique conditions, and also you will work with measurements, drugs, well, medications, and different operations which are done with patients. So that is why we need to understand how to work with this huge, enormous amount of different unique features. And the first look, well, you may think that, okay, I will take the basic data scientist methods like feature importance or, for example, any kind of dimensional introduction, a simple one, PCA, whatever, and I will use it for my purposes. I will take the best or the latent space. But unfortunately, you may find that it's super complex to work with this data because it have a lot of different errors and outliers, and well, you need to prepare it properly. And I'll tell you about, well, a small amount of different problems you may find in this data just for you to be prepared. One of them is that all this data is manually obtained from doctors or some medical services, and that's why there are a lot of mistakes will just made by hand. Well, measurements, units, all kinds of mistakes like, well, it should be 10 times less, but the neurons will put this data, and it's sometimes very complicated to find where it's the real mistake or it's just an outlier, but natural outlier. And well, here will be several distributions of for different features, and it's sometimes not obvious how to work with them. Well, for example, here, as far as I remember, it should be, well, hemoglobin, well, the glycated one, which is widespread to diagnose the diabetes. And here you can see that there are a lot of zeros, well, just in the beginning. Well, there is a small distribution. I suppose that it should be just mistakes in the units. And after that, you see that that is not normally distributed data, but is some kind of combination of different distributions. So that is why it's a little bit complicated to work with it. And more, even if you see that the distribution is okay, it could be outliers and mistakes inside one person. Well, for example, it's normal for a man to have a weight 100 pounds. I don't know, well, 200 pounds sometimes. But if you see that this person was, I don't know, 100, and after the 200, something is not okay. And you should utilize some methods to find these outliers. So what I want to say that this data is the worst type of data you may imagine. Well, because it's made of humans, and it's a very special, because for some cases you will understand that it's a mistake, or you have some medical education, or you have the specialist in your team who could say that, okay, it's not something right. And mathematical methods usually not work properly if you're not in the contact with people who are aware how and why it should be used. So I highly recommend, if you have the project like that, find a business analyst or some consultant from medical sphere, or people should be, well, in your team, or data scientists should be deeply dived into the domain. Well, because sometimes it's complicated, and sometimes, well, you may take different algorithms to find outliers, to find nuns, or whatever, and it will not work properly. Yes, that is. And one more thing that we could imagine, thinking about it, that this data is a super nonlinear, and well, the first thing is that, okay, we could try to utilize the standard approaches to work with data. Well, the kind of, for example, we may try to obtain clusters with some UMAP, or TSNE, or whatever, but it may be not insightful, because the problem is that this data is made by doctors, and doctors are very conservative. And if you want to find the new data, you should utilize some nonlinear and highly nonlinear algorithms, which could provide you with some new insights, non-trivial results. And that is why we start thinking about the BERT model. Well, I suppose that most of the people who work in data science and NLP especially are aware about this transformer, and it's widely used in a variety of applications to the NLP. But the structure of this model and the idea inside it could be used not only for this type of data, but also for example, for EHRs. And one of the points I want to just express today is that you may use different approaches from different spheres of the data science and machine learning, and to apply them to a non-standard variance of data. But how we could use the language model for EHRs? And the answer is we need to construct language. And this language will consist of the visits, the concept, the features, and people inside it. And for example, here is a diagram which was proposed by the people, well, there's a link, well, it's a Nature paper, where they propose how we could construct this language. Well, we just build tokens, which are equivalent of sentences, where you have the patient ID, you have each token will be a visit with some conditions, any kind of medications that were taken, and that is how you will obtain your language. The language will consist of sentences, and sentences is the visits, which have the strong positional connection to what kind of features we try to use. And, well, there are some problems with it, obviously. Well, because if we'll just take this kind of data, it would obtain all the, well, cones from this data, well, because it's very sparse. You will never have the regularly visits, and sometimes even, well, I've seen that it was 2 visits for one person, and they were separated by 10 years, but the features were super connected inside it. And any kind of neural network would say, okay, I think that we should utilize it and to make some predictions based on this connection, which is obviously not sensible at all. And we try to find the new ways how we could modify this kind of language. And the answer is that we could try to utilize the positional encoding, and we will obtain more temporality inside these tokens. When we have the one-by-one visits for each person with all conditions, and positionally encoded. And we obtain this kind of vectors which are more robust for different outliers and mistakes inside data. And on the other hand, it helps us to be consistent of what and how we do with this data. Generally speaking, the BERT, except the tokens inside, is just the same BERT we are using for the language models. And we trained it on the standard variants like MLM and NSP. Well, mask language model, when you get rid of one part, well, if it sends one word, and here in our case it would be one token, and next sentence prediction, well, it's just we try to find what will be the next token. And surprisingly, it was not our purpose, but we obtained the model which could predict what would be the next visit of your patient in clinic. And it's not the main purpose of our project, but it's very interesting that we used it. And really, you could try to do it with all kinds of data if you just invent this kind of language and to use this method. And more. Unfortunately, the classical method of BERT, well, it gives the good results, but we need it to obtain more information and some more variants. And we come to the Siemens BERT as BERT, well, which seems like more applicable to our exact problems. But the other point is that we should map the data. Well, if you're not familiar, well, Siemens BERT is when you have some kind of understanding of the meaning inside the sentences, like it would be relational, or it will be neutral, a question, whatever. And here we need to invent how we'll connect the tokens, sentences, in our own language. And the first idea was that we'll say, okay, we'll construct it like that. We have this sentence, which consists of ingredients and the medications which were taken by a patient, and try to find what will be the list of conditions this person should have. And that works, but unfortunately you could not do it on a very large scale because it's a lot of handwork and it's not super obvious how to do it. So I suppose that this work will be continued, but we'll see. And finally, what we obtain when our model is trained from our kind of language. We have this latent space which represent people or conditions connected to each other. And in this embedding space, well, which is simply just as simple as usual latent space, you could find the insights of how conditions are connected, for example, and you could make the graph of connections between different diseases and to make a classification which is natural, not artificial like it's usually done. And that is, well, once again, something that you could find from this model, but just this graph of different connections. We, in our work, mostly looked at the connections between different patients to find the special groups of people which are needed to be treated differently. But as we know, well, it was a very beautiful presentation a few hours ago about the explanation and the exploratory AI. And I could say that in healthcare, doctors, they love explanations. They could not say that, okay, we have a black box which gives you their results and we always need to obtain some kind of explanation. Attention mechanism, which is inside the transformer, the BERT we use, could be used for these purposes. But if we have a very complicated model, well, as big it is, and it's hard to use it straightforward, and sometimes it's almost impossible. And you always will need some additional techniques. On the next step, when you, for example, you obtain your embedding space, and you, for example, want to find some special groups of people, you could utilize any kind of algorithm for clustering, obtain clusters, and after that you have the sharp or line, what you like, and to find the interpretation of each group of the people. And that is the vital part of each experiment, each project in the medical sphere and the healthcare, that you will need to have these interpretable diagrams. They're also complicated, and some say that they are not absolutely obvious to doctors, for example, but they are much better comparing just to model, which is black box. And I suppose that it is for right now. And well, some main ideas we have today. First, we could obtain a good model which is never been applied to your kind of data, but you could invent a new method. Well, you could just take something from the computer vision, from the NLP, whatever, and apply it to your data. But be careful, you need to understand your data and your domain and everything. And as a sequences, well, the second point is deep knowledge in the domain and the specialist who could help you, well, is a key to make the outcomes valuable for a customer or for your project, whatever. And also, the next is that we need to obtain the validation, and if your model provides you with the answers and you could validate them and obtain the results, well, it's good. If not, you need to find how you could interpret the results. And and finally, yes, remember that the data could be very non-qualified, and you need to do a lot of things just to overcome these limitations. Sometimes with the help of someone, or well, just deep diving yourself. Well, that is all. Well, I suppose for right now, I was not very accurate. Well, not accurate. Well, I'm not deep dive into the technical details, and if you want, you could ask me about it. Well, but it's for general overview. Well, thank you very much. Well, questions?
So, all the medical program needs medical license, yes?
Well, it depends. Well, if you will try to use this model in production for any kind of professional medical recommendation, for example, we have trained our model and we could predict the next step. Yes, you will have need to go to the FDA, for example, United States, to obtain license, and there is, well, evidences that it's possible, so you could do it, and you should provide. Well, it would work like a medical device, so you'll need several stages of trials, medical trials, to prove that it works. Well, if it,
I don't understand. You need a license in any country or?
well, in some countries, maybe not. Well, generally, it's a new domain. Well, if we'll speak about the healthcare, and the legal entities could not make the laws right now to provide. For example, in Russia, we recently, maybe less than 1 year ago, we obtained a new law which makes everyone who wants to insert the recommendation, they call it recommendational systems, into the telemedicine and whatever, you need to obtain the license and to prove that it works like a medical device. And there is a term, it's a special as a electronic medical system, something kind of, and you could go through it with this stuff. But it's complicated. You'll for sure need some lawyers and specialists in this field. Well, and the clinic or doctor who will help you with it. Because, while we work, not on this project, but previously I worked with the different institutions in Russia, and sometimes you will need a person who will be an authority, who could help you to go through this all medical stuff, because sometimes people, it's a new domain, and they will say, okay, this is strange, we don't understand it, we don't understand what we need to do. Well, in the United States, it's easier. Well, for example, there is a tool called ADA, which is licensed in Europe, and you could just enter your conditions, what is going on with you, and they will say, okay, possibly you have this kind of disease and go to that kind of doctor. And they have the license on the European Union. Well, okay, thank you.
Any other questions? Okay, thank you.
Okay, thank you.
Thank